Hello, today we're going to talk about reflections, which are defined to be any transformation where the corresponding parts of the figure and its image are the same distance from the line of reflection along a perpendicular line. So what this means is if I were to draw a line segment connecting the point on the figure and the line of reflection, that the length of that segment would be the exact same as a segment connecting the image point and the line of reflection. Another way to say this is to say that the line of reflection right here acts as a perpendicular bisector of a segment connecting the point and its image. So you can see how our line of reflection kind of cuts in half this line connecting A and A prime. I could do the same thing with B and B prime. If I were to connect those points and cut it exactly in half with the perpendicular line, that line would be this line of reflection. So pretty important thing to know there. Also note that it doesn't have to be a vertex of the triangle. It can be any point, even a point on the inside. If I were to connect that and cut it in half with a perpendicular line, it would create this this line of reflection. So that's the first part of the definition. Another important property of reflections is that they have opposite orientation between the original figure and the image. I noted last time with translations that they preserve orientation, but now if I look at the vertices A, then B, then C in a clockwise manner, after it's been reflected, it's actually the opposite. It would go from A prime to C prime, then to B prime, the opposite order. That's a really important property of reflections, and it's a nice way to test. If you're not sure whether something is a reflection, you can use that to find out. Another important property of reflections is that they are isometries, which is just another word for rigid transformation. I forgot to mention that yesterday, but the big important idea here is that triangle ABC is in fact congruent to triangle A prime, B prime, C prime. You can see that these two figures have the same size and same shape, so reflections preserve that. They are a type of rigid transformation. So let's look at a specific example here of actually finding the reflected image. Here I want to reflect over this line that's horizontal, and we know that it has to be perpendicular, meaning I have to travel vertically, that is perpendicular to horizontal, and the same distance. So point K here is 4 units, so I would need to go 4 units below to find K prime. L would be just 1 unit below this line, and J would be 2 units below. So here would be J prime and K prime and L prime, and if I were to connect those, you'd be able to see we've got a nice congruent triangle that has been reflected over that line. So the big question is, we know how to reflect. That's something we've done for a long time, probably even since elementary school, folding paper and things like that. But the question is, how do we write an algebraic rule for reflections? And we're going to look at some specific examples to figure. So the first thing we need to understand is that it depends on what line we're reflecting over. So we're going to have different rules for different reflections. Let's start by looking at reflecting over the x-axis here on the left. If I have any given point, let's look at some examples. Say I have the point -1, 5. If I want to reflect over the x-axis, which again is a horizontal line, then I'm going to be moving it vertically, so it's perpendicular. It has to be the same distance. So this is 5 units above the x-axis, so I need to go 5 units below, which means A prime would be down at -1, -5. If I try with another point, this point B is about 2 units below, so I need to move 2 units above, and I notice that B prime has the same x-coordinate, but it's at 4, 2 instead of 4, -2. So hopefully at this point you've kind of noticed a trend, and we can generalize, and if not, take a second to think about it. But if I have any point xy and I reflect it, obviously here in quadrant 1 it's going to land in quadrant 4, and its x-coordinate is going to be the same, and its y-coordinate is going to be opposite signs. So that's actually our rule. Our rule is that the point xy becomes the point x, -y. If we're going to reflect across the y-axis, if I take a look here in this middle example here with points F and G, a similar but different thing happens. If I'm reflecting over this y-axis, which is a vertical line, then obviously I'm going to need to travel horizontally. In this case, F is 2 units away, so F prime is going to be at 2, 6. G is 8 units away from the y-axis. So if I travel way out here 8 units, then I see that G prime is going to be at negative 8, 5. So we notice a similar thing occurring here. Even if I have a point down here, if I have some point xy and it travels horizontally, it's not its y coordinate that changes, it's its x. So now we have negative xy, and that's our rule, is that the point xy becomes the point negative x positive y. So these are rules that are always true, and the reflections over the axes are very important ones and pretty simple. But let's look at one that's maybe a little more difficult, like the line y equals x. We've got a few points here, and we notice that this line has a slope of 1, and hopefully we recall that a perpendicular line has the opposite reciprocal slope. So I need to travel at a slope of negative 1 to be opposite reciprocal, to be perpendicular, and if I do that, I notice that this point T at 0, 5 becomes the point 5, 0. Doing the same with R, we would have this point up here. R prime would be at negative 2, 4. Point S here is very close, and it would land right here at negative 3, negative 2 would be S prime. So if you can't tell here, I think it's nice to maybe make a table, or you could draw it with arrows like we do for the general idea. But let's take this down. R prime is at negative 2, positive 4. Excuse me, negative 2, 4. S prime is at negative 3, negative 2. And T prime is I've lost it. Oh, here we go. 5, 0. Alright, so hopefully you can pick up here that these points look very similar. They just have opposite locations. And so it appears that what's happening is that the point xy is becoming the point y, x. The x and y are switching position. And this is our rule for every reflection over the line y equals x for any figure. So there are some basic rules, and we're going to look at some others as we move on. But let's look at some specific examples. Alright, so looking at example 1 here, it's given us the rule. So really we don't need to know what kind of reflection this is, or even if it is a reflection to do this, because all it wants us to do is find the image. But let's take point y, for example, up here at the top. It is at the point negative 4, 5. So according to this rule, the x needs to be multiplied by negative 1, and it should land at 4, 5. That would be our point y prime. X is at 0, 2, and if I change the x coordinate, it's still at 0, 0, 2. E over here is at negative 5, 3, so it should land at positive, that's an E, positive 5, 3. And P should land over here at 3, 1. That should be P prime. So if I connect these points, we see the same, looks like maybe it's a trapezoid, and there's our image, and it is in fact a reflection. If we notice, it's a reflection over the y-axis, which we would hope it would be, because this was our rule we just found a moment ago. So that works. Example 2 here is a little bit more difficult. We are reflecting over a line that is not an axis, so but it shouldn't give us too much trouble. We know it has to be perpendicular, and the line y equals 1 is a horizontal one. So I need to travel vertically, we know, and it's just a matter of finding the correct distances. So n, for instance, is 2 units below the line of reflection, so I need to travel 2 units above, and that's where n prime should be. D is 3 units below if I count, so I should move up 3 units to find D prime. R here is 1, 2, 3, 4, 5 units below, so if I travel 5 units above, it's actually not going to fit, but we can eyeball it, and there would be R prime. And Z here is 4 units below, so if I travel 1, 2, 3, 4 units vertically, then there would be Z prime. And we see that that there's our figure. And also notice, I keep forgetting to mention this, but the orientation is opposite, right? So if we go from N to Z to R to D, clockwise in our original figure. If I start at n, it's the exact opposite going clockwise, from d prime to r prime to z prime. So we can see that's another nice way to test whether it is a reflection, and it fits here. I could make this a tad bit more difficult by asking you to find the rule for this reflection, but I'm going to leave that for classwork and let you guys work on that. Let's look at a third example, though. Here we have the figure and its image, and we have to describe it and find a rule. So it looks like maybe this has been a reflection, but let's test it. Let's look at the orientation. So in my original function, it goes from B, U, D, then K. And if I check my image, it seems to be the exact opposite. It's B, then K, then D, then U. So that does work, so we will say it's a reflection. And since we know it's a reflection, we need to find the line of reflection. So we can do this a couple of ways, but again, if I were to connect the points, any point in its image, and then try to cut that in half with a perpendicular line, so maybe something like this, that should be our line of reflection. And obviously I can't draw a straight line, but I hope that it's clear at that point that this is a line with a slope of -1 and a y-intercept of 0, so that happens to be a reflection over the line y equals -x. Just went ahead and wrote the rest of the coordinates down. So take a second and see if you can see a relationship, how these original points on the left in our pre-image have been transformed. We obviously have been reflected, but what is actually happening between the original coordinates? And hopefully you can see that they seem to be changing location, switching. The x goes to y and vice versa. But there's something else going on here. Notice that all the negative coordinates in my pre-image became positive here. And so the rule for reflection over y equals -x is that, yes, they change position, but they also both become negative. So that would be our rule for any reflection over the line y equals -x, and that's the answer for this equation.